The primary way to build applications with the RMP motion controller is the RapidCode API, which provides flexibility in commanding motion for production-level development. But many users would like to explore the RMP motion controller without writing any code. RapidSetupX is a cross-platform tool that enables you to configure your EtherCAT network, monitor your system, and leverage complex features of the RapidCode API through a graphical interface. In this video, we'll walk through getting started with RapidSetupX, from creating a controller all the way up to spinning a real axis. Before beginning, ensure that you have installed and licensed RMP and verified that it can run properly on your machine. An industrial PC from RSI, such as the IPC400, will often have the required software already installed. For testing hardware, ensure you have a spare network interface card, an EtherCAT compatible motor drive supported by RMP, and an Ethernet cable to connect them. Our list of officially supported EtherCAT nodes, as well as a guide to using unsupported nodes, is linked in the description. If you are unfamiliar with RMP or need clarification on these prerequisites, it is recommended that you visit our support site, also linked below, for documentation and guides. RapidSetupX can be downloaded from our portal, separate from the main RMP installer. Click the download link corresponding to your operating system and architecture, then unzip this folder to reveal the RapidSetupX executable and its required files. We recommend creating a shortcut to this executable for the sake of convenience. Rather than communicating directly with the motion controller on your machine, RapidSetupX works by sending requests to a process called RapidServer, which translates these requests into the corresponding calls to the RMP firmware. This enables remote and even cross-platform operation through RapidSetupX. We'll demonstrate here the simplest case of connecting to a local RapidServer on the same machine. Start RapidSetupX, which will open to the servers page. Here we can see the different options we have to connect to a RapidServer. On Linux machines, a RapidServer should be running automatically as a service, and can be connected to in the Discovered RapidServers section. On Windows, you must start a RapidServer manually. The launch option will do this conveniently within RapidSetupX, but you may also start the process externally. Once you have connected to a RapidServer, RapidSetupX should automatically navigate to the controller page. On this page, you will configure and start your instance of the RMP motion controller. Windows users must specify the in-time node that RMP will be running on and the path where your RMP installation lives. If RMP is installed in the default location, this field can be left blank. On Linux, you must specify the primary network interface card for EtherCAT communication, which can be chosen from this dropdown, and the isolated core that RMP will be running on. If your license is not found, verify that you have obtained the license file from Rapid Portal and use the Copy License to Server button. Now we can create the RMP motion controller. The page will be updated with information about this controller, including the current RapidCode object counts. Changing these object counts will invalidate all previously obtained RapidCode objects, so make sure to always set them before moving on to the rest of your application. Let's begin by modifying the axis count to give ourselves one phantom axis. An axis object represents a single axis of motion control. These can either be hardware axes, which represent real motors attached to EtherCAT nodes, or phantom axes, which are software-only virtual motors. Let's begin by spinning this phantom axis before moving on to a hardware one. Navigate in the tree view to the created phantom axis to bring up the axis page. In the Overview section, we can set a user label for this axis for easier navigation. In the Motion section below, we can see the monitored position, velocity, and acceleration. Under Position, there are two fields, Command and Actual. Command position is generated every sample by the RMP firmware to tell the axis where it's supposed to be. Whenever you command motion, RMP generates a series of command positions, incrementally taking your axis to the target you specified. Actual position uses the measurement from your motor's encoder to best estimate the true position of the axis. When commanding motion, RMP will collaborate with your motor drive to have this follow the command position, but it won't be perfectly one-to-one. Being simulated, phantom axes don't have a physical motor or drive. Therefore, they have no actual position, and this value must be considered meaningless. Keep this distinction in mind when configuring or monitoring motion. The Limits and Actions section defines safety precautions, which can be configured to halt motion if the axis breaches predefined limits. Most of these don't have much meaning for phantom axes and can be ignored in this simple example. The position error limit, however, requires attention. Position error is the difference between the command position and the actual position. Since phantom axes have no actual position, this error value is meaningless here, and should not be used to halt motion. However, for demonstration purposes, let's leave it enabled, and set the trigger to a smaller value. Now we can move on to the motion parameters section. First, let's specify the move type. An absolute move sends the motor to a specific position measured from the origin. A relative move moves the motor some distance from the current position. A velocity move accelerates the motor until reaching a final specified velocity, which it will sustain until stopped. Let's configure an absolute move, and leave the target positions as they are, adjusting our other motion parameters to prevent the move from being particularly slow. We won't adjust the final velocity or jerk percent in this example, but you can read more about these motion parameters in our S-curve motion documentation. To start the phantom axis motion, enable the amplifier, then click the right arrow button to send the axis forward. Unfortunately, the position error limit we left enabled causes this motion to be aborted. This is why it must be disabled for phantom axes. Click Clear Faults to return the axis to an idle state, then disable the error limit by setting the action to none. Now we can command the motion again and see our axis complete its full journey to 500 units. Notice that even though the error limit triggered again, setting its action to none prevented it from interrupting the motion. Let's use the left arrow to send the axis back to the origin. Once the motion is done, we can disable the amplifier. Nice job! You've just commanded your first motion with RapidSetupX. Let's remove our phantom axis from the motion controller and move on to commanding our first real axis. Navigate to the network page from the tree view. Right now, the network is uninitialized, and no information is being sent to or received from your drives. Click the Discover button to give RMP information about the connected nodes. If the node count fails to update, verify that your drives are powered on and connected. Now, generate the EtherCAT network information file, or ENI file, which determines the topology of the network that will link these drives together. Once this is done, we can start the network and obtain access to our hardware axes. This can take a bit of time, so don't be alarmed if the network doesn't reach operational state instantly. If your network fails to start, take a note of the last start error and any information in the network log. For troubleshooting advice, try browsing our community forum for similar issues. Your connected nodes will now be displayed in the tree view. By clicking on the name of your drive, we can access the network node page, which displays information about the specific node you have connected. For now, let's navigate once again to the axis page. Notice that the overview section now lists the name of the node that the axis is attached to, rather than the phantom icon. The hardware axis will also have an actual position, which we can verify by manually turning our motor and watching the value update. You may notice that this value quickly surpasses the 500 unit destination we used for our phantom axis. By default, position is measured in terms of one encoder count per unit, and modern encoders can have thousands or millions of counts in a single revolution of the motor. User units make commanding motion at this scale easier by changing the number of encoder counts per unit. Let's define our motion in terms of revolutions. Obtain the counts per revolution of your encoder. Then enter this value into the user units field. To verify, zero the position of the axis, and rotate the axis a full revolution. The resulting actual position value should read around 1.0, indicating that 1 unit is now equal to 1 revolution. Note that you can also use this process to estimate the counts per revolution of your encoder, if you don't know the exact value. Now that we're working with real hardware, it's important to carefully examine our limits and actions to ensure the safety of the equipment and ourselves. Since our hardware axis has a meaningful actual position, it's essential that we keep the position error limit enabled. I'll leave the action as is, and set it to trigger at an error of half a revolution. The amplifier fault can indicate many kinds of problems on the motor drive that get reported to RMP, so let's leave it enabled. The home switch is not relevant for this example, but can be read about more in our documentation. The positive and negative hardware limits must be configured with external input triggers, such as a switch at the end of a linear rail. Since we don't have these with our simple motor setup, we won't need to configure them. Similarly, the positive and negative software limits will trigger if the motor surpasses a certain actual position. Since our motor is free spinning and doesn't need its range limited, we can leave these at the extreme values they're at by default. Now that our axis has been configured, we're ready to once again command motion. Let's select the relative move and specify an increment distance of 3 revolutions. Let's set our other motion parameters to more reasonable values for our updated user units. Feel free to adjust these parameters once you're comfortable. Make sure that you have enabled the amplifier on your physical motor, then enable the amplifier in RapidSetupX. Click the right arrow to move the axis 3 revolutions forward. Since this move is relative, you may repeat it a few times or move in the opposite direction. When you're done, disable the amplifier, shut down the network, and shut down the controller. Congratulations! You've just commanded motion of your first real axis using RMP. Hopefully now you feel confident in your ability to understand and command basic motion in RapidSetupX. More complex features such as multi-axis setups, motion with user limits, and plotting data with recorders are beyond the scope of this video, but we encourage you to explore our documentation to learn more about the many ways to use RapidSetupX. A link to relevant pages can be found in the video description. For users wanting to know more about the many potential uses of the RMP motion controller, try exploring our blogs, demos, and documentation for example projects. For users interested in building production-level applications with the RapidCode API, see our sample apps and introductory video linked here. Thank you for watching, and enjoy commanding motion with RMP.